Find the maximum area of a triangle inscribed in a semicircle of diameter 40 centimeters. Okay, so it's 40 across here, and this is a triangle. A triangle inscribed in a semicircle is always a right triangle. So whether you do this or, one second, if you draw any triangle in a semicircle, you can't help it. You're going to end up with a 90-degree angle. There's one there. I'll try another one. Da, da, da. Measure that angle, you'll get 90 degrees. It's 90 no matter what. That's just a neat property that semicircles have. So that means these triangles are always right triangles, which means the Pythagorean theorem always holds. That's probably going to help us at some point here. And what they're asking for is maximum area. So we need some way to connect area to the size of this triangle. Well, the measurements of this triangle are 40, obviously. We can't do anything about that. And we have these other two sides, which I'm going to call A. Whoops. They already have labeling on there, so I should probably go with it. If this is angle A, then this is side A. And if this is angle C, then this is side C. That's going to make the Pythagorean theorem look a little weird, but that's okay. We're in calculus, we can handle it. The Pythagorean theorem says that the relation between these sides is a squared plus c squared equals 40 squared. That's probably going to help us in a bit. And the other thing that we know about this triangle, if we're trying to find its area, the area of a triangle is base times height divided by 2, or 1/2 base times height. So here it's 1/2. The base and height of this thing would be A and C in whatever order you want. I'm going to put them in alphabetical order. So that's our area. There's our base if you turn your head far enough to the right, and here's our altitude for the triangle. This is what we're trying to maximize. And you've probably seen this before. We want to take a derivative here, but we have two variables. We have to get rid of a variable. Here's this other equation to the rescue. We can use this to get rid of either A or C, because we can say c squared equals 1600 minus a squared, and then we can say c is the square root of 1600 minus a squared. Where we used to have c here, we can put this in its place. 1/2 a, and then c is all this. Or actually, because I'm a little tight on space, instead of that root, I'm going to put brackets to the 1/2 power, because we have to do a derivative, and I can't burn a lot of screen space on recopying this thing over and over. So this is our area, and it's kind of an ugly expression, it turns out, but this is how we get its area just in terms of one of its sides. And now if we want to optimize this, you know the drill. Let's differentiate it and then set the derivative equal to 0. So if we do that, we get, I didn't think of this, we get dA. Weird. Equals, now how do we do the derivative here? This is a product with a first part and a second part, and so we get to do product rule. So this is going to be a pretty impressive derivative. We're going to get first, derivative of the second is 1/2 1600 minus a squared to the minus 1/2 times, and the derivative inside here is minus 2a. So all this is first d second, and now we do second. D first, and the derivative of the first is just 1/2. Can we clean that up? Can we factor it? Well, let's collect terms at least before we go on here. We have 1/2 times 1/2 times minus 2 comes out to minus 1/2. times another a is a squared, and then we have 1600 minus a squared to the minus 1/2, yuck. And for this next term we just have, it's much simpler, 1/2 1600 minus a squared to the positive 1/2. This has common factors in it. We can take out a 1/2. In fact, I'd like to take out a minus 1/2 so that this leading term goes positive. We can also take out 1600 minus a squared to its lowest power, which is minus 1/2. So, big line coming up. We take out minus 1/2. What are we left with? This minus 1/2 is completely gone. We're left with a squared. Oops, sorry. Before I get into that, we take out minus 1/2, and we're also taking out 1600 minus a squared to its lowest power, which is minus 1/2. Okay, now I can dig in. Minus 1/2, completely factored out, it's gone. The a squared is left behind. 1600 minus a squared to the minus 1/2, completely factored out, so that's gone. On to the next term. 1/2 divided by minus 1/2 leaves minus 1. And then we get 1600 minus a squared to the power of, how much? 1/2 minus negative 1/2 comes out to positive 1. So, I need more room. I'm going to get rid of the Pythagorean theorem here. I'll continue up here. So we have minus 1/2, 1600 minus a squared to the minus 1/2. And inside the brackets we have a squared minus 1600 plus a squared. So, minus 1/2, 1600 minus a squared to the minus 1/2. In the square brackets we get a squared plus another a squared is 2a squared. And one last time, minus 1/2, we have 2a squared minus 1600 over 1600 minus a squared. This is because we had 1600 minus a squared to the minus 1/2. The minus means put me in the denominator, and the 1/2 means square root me. So there we go. And all that equals 0. Now if you go to solve this, the obvious place to start is multiply it by its own denominator, both sides. And when you do that, it simplifies a bunch. You get 2a squared minus 1600 equals 0, which means a squared equals 800, which means a is like 28.3, I seem to remember. Yeah, a is 28.3. Now if you go back using the Pythagorean theorem and see what that gives you for the length of c, you'll find that that length is also 28.3, which means the optimal triangle is an isosceles triangle. It's one where the sides A and C are exactly the same. They're both 28.3s, and that will give you the greatest possible area.